Hey everyone, welcome to today's video where we're going to dive into one of the most fascinating logical puzzles ever discovered. Imagine finding a single question so powerful it could threaten the entire foundation of mathematics. That's exactly what happened when Bertrand Russell discovered his famous paradox back in 1901. So grab your thinking caps, maybe a cup of coffee, and let's explore this incredible story that connects math, philosophy, and even the way we use language. Trust me, by the end of this video, you'll never look at sets or logic itself the same way again. What is a number anyway? Let's start with a seemingly simple question. What exactly is a number? Take the number 4. I'm not talking about 4 apples or 4 cars. I'm talking about 4 itself. We know all sorts of things about it. It's divisible by 2, it's the square root of 16, and it's 1 more than 3. But what actually is it? This isn't the Arabic numeral 4 that I'm writing, that's just a symbol representing the number. The Romans used IV to represent the same concept. The number itself is something abstract that no one has ever seen or touched, yet it's absolutely essential to science, technology, and basically all of human civilization. In the 1700s, the Prussian philosopher Immanuel Kant suggested that mathematics was simply a construction of the human mind, making mathematical truths somewhat subjective. But this idea didn't sit well with everyone. The German philosopher Gottlob Frege and the English philosopher Bertrand Russell had a different vision. They believed mathematics had to be objective and universal. To counter Kant's view, they developed a perspective called logicism, which proposed that mathematics was actually a branch of logic. Specifically, they thought arithmetic, the most basic form of math, could be reduced to first-order logic and something called set theory, their ambitious goal, to definitively answer the question, what is a number, with a precise logical definition. Numbers are sets, set theory a crash course. So what exactly is a set? Simply put, a set is a collection of objects. The mathematical study of sets was pioneered by Georg Cantor in the 1870s, and it quickly became fundamental to modern mathematics. Cantor's work on set theory led to some mind-blowing discoveries, like proving that some infinities are actually larger than others. Yes, you can have an infinite collection of things, and then another infinite collection that somehow contains more things. Math is wild. Let me introduce you to naive set theory, which is just the intuitive way we think about collections of things in everyday language. Set can contain anything you can think of. The set of all cats in the world, the set containing LeBron James and the top half of the Eiffel Tower, the set containing LeBron James and Harry Potter. Yes, sets don't care if their members exist in real life. Even the set of all things that cannot be imagined, which paradoxically contains things we can't even think about. We write sets using curly brackets. Okay. For example, LeBron James 4 is a set containing 2 members, a basketball player and a number. For larger sets like the set of all cats, it's impossible to list every member, so we use a different notation. X is a cat, which reads as the set of all X, such that X is a cat. Sets have some important properties. Unrestricted composition. You can make a set out of any collection of things you can imagine. Identity through membership. A set is defined solely by what's in it, not how you describe it or the order of its. Elements order doesn't matter. 1, 2 is the same set as 2 1s. Repetition doesn't change anything. 1, 2, 2 is just the same as 1, 2. Description doesn't matter. The set containing just LeBron James is the same as the set containing the all-time NBA scoring leader, if that's LeBron. Sets can be combined. The union of any 2 sets is also a set. Subsets are sets. Any collection of members from a set forms another valid set. Singleton sets. A set can have just one member, called a singleton set. Empty sets. A set can have no members at all, called the empty set or null set, written as gowns or sets of sets. Sets can contain other sets as members. This last property was crucial to Frege and Russell's project. They believed that the number 1 was actually the set of all singleton sets, the number 2 was the set of all sets with 2 members, and so on. the paradox that changed everything. But then we come to Rule 11. Sets can contain themselves. This seems reasonable given Rule 1, unrestricted composition. After all, if we can make a set out of anything we can think of, and we can think of sets, then we should be able to have sets that contain themselves. Some sets clearly don't contain themselves. The set of all cats doesn't contain itself, because it's a set, not a cat. The singleton set containing LeBron James doesn't contain itself. It contains only LeBron, but some sets do contain themselves. The set of all sets must contain itself, since it is a set. The set of all things I'm thinking about contains itself when I'm thinking about it. In 1901, Russell was pondering these self-containing and non-self-containing sets when he had a brilliant but troubling insight. He asked, what about the set of all sets that do not contain themselves? Let's call this set R. X is a set, and X does not contain itself. Now comes the mind-bending question. Does R contain itself? Let's analyze both possibilities. If R does contain itself, then it must satisfy the condition for membership in R, but that condition is does not contain itself. So, if R contains itself, then R doesn't contain itself. Contradiction. If R does not contain itself, then it satisfies the condition for membership in R, so it should be included in R due, which means R contains itself. Contradiction again. No matter which way we answer, we get a logical contradiction. R both contains itself and doesn't contain itself. This is Russell's paradox, and it sent shockwaves through the mathematical community. Russell communicated this devastating finding in a letter to Frege on June 16, 1902. The timing couldn't have been worse. Frege was just finalizing the second volume of his life's work, which was built entirely on the foundation of set theory. Upon reading Russell's letter, Frege was so distraught that he reportedly had a breakdown. Their grand project to define numbers as sets was in serious jeopardy. The attempted fix, the obvious solution, might seem to be, let's just change the rules. After all, aren't mathematical axioms just made-up rules anyway? That's exactly what Russell and other mathematicians tried to do. They developed more restrictive versions of set theory, like Zermelo-Frenkel set theory, that essentially banned sets from containing themselves. This meant sacrificing rule number 1, unrestricted composition, to avoid the paradox. But there's a deeper problem here. The rules of set theory weren't just arbitrary inventions. They were attempts to capture how we naturally think about collections of things. When we talk about all the cats in the world or the pile of potatoes, we're using set-like concepts in our everyday language. The deeper problem, language itself. This is where Russell's paradox gets even more profound. The problem isn't just with set theory. It's with the fundamental structure of language and thought. Consider how we make statements about things. In linguistics, this is called predication. When we say Garfield is a cat, we have a subject, Garfield, and a predicate is a cat. The predicate says something about the subject. Just like sets can contain sets, predicates can be applied to other predicates. Is a cat is a predicate. We can ask, is a cat a cat? No, it's not. It's a predicate. We can ask, is a predicate, and yes, it is. Some predicates are true of themselves, like is a predicate, or is made of words, while others are not true of themselves, like is a cat, or tastes, like chicken. Now let's try to create a predicate that's true of all predicates that are not true of themselves. This predicate would be, is not true of itself. The crucial question is not true of itself true of itself? If it is true of itself, then it isn't true of itself. If it isn't true of itself, then it is true of itself. We've recreated Russell's paradox in ordinary language. This reveals something profound. The paradox isn't just a quirk of mathematical set theory, it's embedded in the very structure of language and logic itself. We can't simply fix it by changing the rules of set theory because it emerges from how we think and talk about the world. Why this matters? Russell's paradox isn't just an abstract puzzle. It had profound implications for the foundations of mathematics, logic, computer science, and philosophy. It forced mathematicians to be much more careful about their foundational assumptions. It led to the development of type theory, which influenced the design of programming languages. It showed that self-reference can lead to logical problems, which influenced later work on Gödel's incompleteness theorems, another devastating blow to the dream of establishing mathematics on absolutely certain foundations. Perhaps most importantly, it revealed that even our most basic logical tools can contain hidden contradictions. The rules that seemed most obvious and natural, like the ability to form any collection we can think of, turned out to harbor profound problems. Modern mathematics has found ways to work around Russell's paradox through various axiom systems that restrict what kinds of sets can be formed. But the deeper philosophical issues about self-reference, the nature of language, and the foundations of logic remain with us today. The lasting legacy Russell's paradox reminds us that even the most fundamental aspects of our thinking can contain hidden contradictions. It shows how a single seemingly innocent question can undermine entire systems of thought. In our age of artificial intelligence and increasingly complex logical systems, Russell's insights remain vitally important. Self-reference and recursive definitions are everywhere in computer science and formal logic. Understanding the paradoxes they can generate helps us build more robust systems. More philosophically, Russell's paradox reminds us to be humble about what we can know with certainty. Even the most basic logical structures we use to understand the world might contain hidden contradictions or limitations. The next time you think about collections of things, whether it's your shopping list, the set of all prime numbers, or the collection of all collections, remember Russell's mind-bending question that shook the foundations of mathematics. Can a set contain itself? And what about the set of all sets that don't contain themselves? That's it for today's deep dive into Russell's paradox. I hope you enjoyed this journey through the foundations of mathematics and logic. If you did, please hit that like button and subscribe for more mind-expanding content. Let me know in the comments if you've encountered other fascinating paradoxes or if you have questions about this one. Until next time, keep thinking critically and don't be afraid to question even the most fundamental assumptions. Thanks for watching.